I'm going to make a glass mouse this afternoon, and we're starting out here with a big open flame. So that's where we get that name, Flamework. The torch that I'm using is burning a combination of natural gas and compressed oxygen, and that'll produce a flame somewhere in the 2,000 to 5,000 degree Fahrenheit range. It's a very adjustable flame, and that's why that range is so large. So I can change the flow of the oxygen and the gas independent of each other, changing the size and shape and temperature of the flame quite a lot as we go along. When you melt glass, it's going to soften up and flow pretty naturally into a round shape. And so we start out with a round shape, which we call a gather. So I've got my gather of glass. I'm letting it cool so that it firms up. And in the meantime, heating some glass to a higher temperature to make a leg. And that way I can attach it and stretch it. Glass is really stretchy when it's hot. If you melt it and then pull on it real quickly, you can stretch it right into a thin thread. And when I'm making a little bit thicker shape like I do for a leg, I will pull it kind of slowly so that it has time in the air to cool off, so it will firm up. It's going to soften and harden really gradually as it's heated and cooled. So compared to other materials that you can melt, glass has a really long working time, and that makes it really versatile for shaping. You'll see a real bright glare coming from the glass as I'm heating it. That's called soda flare. It comes from an ingredient in the glass which is called soda ash. So there's a little bit of sodium from the soda ash actually burning away as that glass melts. And that creates the soda flare. So soda flare, it's not harmful to our vision, but it is kind of hard to see through it. And that's why we have some filters around the sides and the front of the booth here. They're called didymium filters. Didymium is a combination of a couple different rare earth elements, and they will filter out the specific color wavelengths of light, making that soda flare, so we can see through it and see the surface of the glass. You might want to take a look through the filters and then compare that to what you see through the unfiltered glass. There's quite a difference there.
There's the
I've
filters.
got a similar filter in my eyeglasses,
There's no filters.
and that also allows me to see the surface of the glass. Very useful when I'm trying to shape it. And I'm working with different parts of the glass at different temperatures as we go along, but when I join the bits of glass, I need them both to be, both the surface is hot. So I'm heating glass here for a tail, and then just before I attach it, I'll heat the spot that I want to attach it to. And with both those surfaces hot enough, the glass flows together. So this forms a nice stable connection. This is called a hot seal. That's a permanent connection. It's practically seamless because those parts have actually flowed together there, and it really all becomes one piece of glass. So that's the lower part of the mouse, and the next thing I want to work on is the head. To do that, I have to melt the handle off there. Now, glass is a really insulative material. I bet you already guessed that. I'm heating the end of this glass rod up to 3,000 degrees. That's the melting temperature of this glass. It has a high melting temperature because of its formula. And so 3,000 degrees at the end of the glass rod, but I'm holding on to it in my bare hand, just inches away from that molten glass. So the reason I can do that is that heat doesn't travel through glass very fast. And so the part of the glass rod that I hold on to, that's actually still room temperature. But then for the same reason, the glass that I've melted to shape it is still really, really hot. So it takes a long time for heat to soak into glass, and once you get it in there, it takes a really long time for it to soak out again. And so I've put a temporary handle onto the foot of the mouse in order to start shaping the head, because although the body of the mouse is hard right now, it's really hot. It's about 1400 degrees Fahrenheit, so I wouldn't be able to grab that with my hand. And in fact, it's going to be way too hot for me to touch it for 10 or 15 minutes, even if I stop heating it right now. So that's because of the insulative quality of that glass. So I've got the hot seal, which I used for the legs and the tail. That's the permanent connection. But this handle that I put on the foot is just a temporary handle. And so I've used something there called a cold seal. And that means that I did heat the glass up, but only enough to make it kind of sticky. So it's sticky enough that I could tack it in place on the foot, but not liquid. And so those parts didn't flow together, and they did not make a stable bond. It's very, very fragile. And it's going to get more fragile as it cools. If I leave that alone long enough, that handle will actually drop right off of there. So I need to get my shaping done before the handle gets cool enough to fall off of there. Usually I can do that. So we'll let the head cool a little bit. I'm going to add some glass for the front legs. This glass that I'm using is called borosilicate, and there are lots of different types of glass. They're going to have different characteristics. Often those are determined by different ingredients in the formulas. So this is a glass that's formulated specifically to be resistant to thermal shock. And what that means is objects made out of borosilicate glass can withstand fairly dramatic temperature changes compared to other types of glass without breaking. And that makes it a really useful glass. This is used for things like scientific labware. So you'll often find test tubes and beakers made of borosilicate, and coffee pots and baking dishes. So there are a lot of places where glass needs to withstand extreme temperature shifts, and borosilicate does that really well. It's the boron in the formula that allows it to do that. And then we talked also about the soda ash. That's producing the soda flare. The formula in general is what's making this melt at such a high temperature. And so it's the chemistry of the formula that really gives the glass its particular characteristics. And that applies to color as well. When you want a different color of glass, you will add different metal oxides to the formula and get different chemical reactions between those oxides and the other glass ingredients. And an oxide that you would be familiar with is rust. So what we normally think of when we say rust is specifically iron oxide. And when you put iron oxide into your glass formula and you melt it in, the glass turns green. So that's the chemical reaction between the iron and the other glass ingredients. If you want some black glass, for instance, like I'm going to use for the nose and the eyes, you need a different chemical reaction, and so you put in some manganese oxide. So different oxides from different metals are going to give you the different colors. When I'm working inside the Flameworking booth here, I won't actually be able to hear you if you have questions. There's just enough noise in here from the sound of the ventilation fan that's over my head, and then also the sound that the torch makes, that it's sort of muffled in here. It's not exactly loud, but it's just a sort of whooshing sound from the torch and the fan. And so I can't really hear words when I'm in here, but if you're starting to think of questions for me, I hope that you'll save them. This mouse is pretty close to being done. And when it's done, I'm coming out of the booth, and I'd be really happy to answer any questions you have then. It's pretty cold out today, so we're going to give this mouse a scarf, a little bit of green glass. When glass is heated and cooled, it swells and shrinks. It swells when it's heated and shrinks as it cools. So if you think about the temperature of the mouse right now, you can imagine there's actually a huge range of temperatures there. There might be 1,500 degrees difference right now in temperature between the head and the feet. And that means there's some stress building up in the glass because different parts of it are tugging against each other as they swell and shrink. So we call that thermal stress because that has to do with the change in temperature. So thermal stress. If you leave too much of that stress trapped in the glass, it will actually pull the glass apart. It will make it break. And so once the shaping is done, we need to relieve some stress from our glass. And we do that by a process that's called annealing. Annealing is a word you hear a lot in the Glass Museum. It's a really important part of the finishing process for the glass. And it can be accomplished in a couple different ways. But the key to annealing is that you want to even out the temperature of the glass within its particular annealing temperature range. So that's different for different glasses. And for this glass, that's going to be about 1,000 degrees Fahrenheit. At that temperature, the glass is hard. It's not going to change shape at all during its annealing process. But the molecules in the glass at that temperature are vibrating. And they vibrate fast enough that they will realign themselves. They can actually settle themselves into a less stressed arrangement during the annealing process, and that stabilizes the glass. Once it's stabilized, it's still really hot. It's going to be about 1,000 degrees. So it's in a stable molecular structure, but it's hot, so it has to cool off. And if it cools really fast, it's going to reintroduce thermal stress. So we do the whole annealing cycle, that annealing where we even out the temperature, and then a really slow cooling process over a number of hours. We do that in a computer-controlled annealing oven. And I have the oven under the shelf over here, so this mouse and all the other pieces I make today are going to go in the oven eventually. But you remember toward the beginning I was talking about borosilicate and the fact that it's so resistant to thermal stress. So that's the kind of stress we're talking about here. And unlike other types of glass that would have to go into the annealing oven immediately once the shaping was finished, we can use a very minimal type of annealing with this glass, which is called flame annealing, and that's this here. So I've lowered the temperature of the flame. I'm going to even out the temperature of the mouse a little bit just by warming up the coolest parts. The hottest parts are cooling down right now. This is a very minimal and imprecise method of annealing, but it's enough for the borosilicate to stabilize it enough that we can leave it sitting out on the table now. And that's kind of unusual. If this was standard soda-lime glass and I left it sitting out, it would break just within a number of minutes. But the borosilicate is particularly resistant in that area of temperature change, and so we like to show that off by leaving the piece sitting out on the table. So you can see how strong the borosilicate is, but then that also, as a side benefit, allows us to see the details of the mouse before it goes into the oven. And once it goes in the oven, it's not coming out again until tomorrow. So that was flame annealing. Just going to smooth out the texture of the scarf a little bit here, then we'll take this off the handle. So remember the cold seal is that handle here. Very delicate attachment, so just a little tap on the side of the torch releases that handle. And then that is our little glass mouse with a green scarf. So thanks very much for watching. If you have questions, thank you. If you have questions, I'll come out of the booth to answer them for you. And have a lovely afternoon.
Cái dòng nhậu này của em mẹ đi đi tụi em.